Welcome to the first lesson in the series of lessons on electrode potentials from the OCR Chemistry A-Level specification. Today we're going to cover standard electrode potentials. Firstly, we're going to cover a bit of background information about redox equilibria that will help us understand the rest of the topic. We will then go on to define the term standard electrode potential, which is given the symbol E, and describe how to measure, using a hydrogen electrode, standard electrode potentials of metals or non-metals in contact with their ions in aqueous solution, and ions of the same element in different oxidation states. And finally, we're going to use standard electrode potentials to compare the oxidizing and reducing abilities of different chemical species. Let's begin by looking at some definitions you should be familiar with from AS chemistry. Oxidation is an increase in oxidation number or the loss of electrons. Reduction is a decrease in oxidation number or the gain of electrons. A redox reaction involves both reduction and oxidation and results in one or more electrons being transferred and is accompanied by changes in oxidation state. Oxidizing agent is a substance that brings about oxidation by accepting electrons from a reactant being itself reduced, and a reducing agent is a substance that brings about reduction by donating electrons to a reactant being itself oxidized. So to redox equilibria. When a piece of metal is placed in an aqueous solution of its ions, a chemical equilibrium is set up. The forward reaction involves the metal atoms losing electrons and entering the solution as positively charged hydrated ions. This leaves a layer of electrons on the surface of the metal. It is an oxidation reaction and can be represented by the half equation M solid reacts to form M plus aqueous plus E minus for a single positive ion such as sodium. This is the example shown in the slide. The backwards or reverse reaction involves the hydrated metal ions gaining electrons from the surface of the metal and being deposited as metal atoms on the surface. This is a reduction reaction and is represented by the half equation M plus aqueous plus E minus reacts to form M solid for a single positive ion such as sodium shown in the slide. If it was a 2+ ion, such as copper, it would gain 2 electrons from the surface of the metal. Redox equilibria is established when the rate of oxidation is the same as the rate of reduction, i.e., the rate at which metals lose electrons and enter the solution is the same as the rate at which metal ions gain electrons and are deposited as metal atoms on the surface of the metal. The position of the equilibrium, and hence the relative charge built upon the surface of the metal, depends upon the ease at which the metal atoms lose electrons and turn into ions. The greater the tendency of the metal atom to lose its electrons, the further to the right the equilibrium lies. The greater the build-up of electrons on the surface of the metal, and the more negative the metal electrode becomes. For example, when a piece of zinc is placed into a solution of zinc sulfate, the equilibrium lies to the right-hand side. The overall reaction means there is a build-up of negative charge on the metal, some of the metal has disappeared, and the concentration of zinc ions in the solution has increased. The opposite is true for copper. The equilibrium lies on the left-hand side, and the overall reaction means that the copper ions in solution take electrons from the surface of the copper metal and are deposited on the surface, leading to a build-up of positive charge on the metal, an increase in the mass of copper, and a reduction in the concentration of the copper ions in solution. Now for the explanation of the term electrode potential. The surface of the metal and the solution have opposite charges, one positive and one negative, and because of this difference in charge, a potential difference exists and is known as an electrode potential. The greater the difference in charge, the greater the electrode potential. The difference in charge depends upon the position of the redox equilibrium that is set up. The greater the tendency for the metal atom to lose its electrons, the more negative the metal electrode becomes. A half cell is made when a metal is placed in a solution of its own ions. There are 3 different types of simple half cells that you need to know about. Number 1, metals in contact with their own ions in aqueous solution, as we've just seen in the examples before. Number 2, non-metals in contact with their ions in aqueous solution. And number 3, ions of the same element in different oxidation states. In all of these examples, a redox equilibria is set up and there is a difference in charge. This difference in charge is the electrode potential of that half cell. Any 2 different half cells can be joined together to form a whole cell, and the electrons will flow. This transfer of electrons will allow a redox reaction to occur, with one half cell providing the electrons and acting as the reducing agent, and the other half cell accepting the electrons and acting as the oxidizing agent. In the example shown on the slide, the copper-zinc half cell, the zinc has a greater tendency to lose electrons and so acts as the reducing agent. The zinc electrode is the negative electrode. The electrons flow from the zinc half cell to the copper half cell, which is the oxidizing agent, and accepts electrons. The voltage measured will be the difference between the 2 electrode potentials. In order to measure the electrode potentials of different half cells, we need to make something 0, so we can compare all other electrode potentials to this. So it was decided that the standard electrode potential of the standard hydrogen half cell was 0 volts, and all others are measured compared to this. The standard hydrogen electrode is the internationally agreed reference electrode. It is shown on this slide. You may well be asked to label a diagram of this half cell. The cell has hydrogen gas in equilibrium with hydrogen ions. The cell consists of hydrogen bubbling over an inert electrode. This is simply because at 298 Kelvin, hydrogen is a gas. The inert electrode provides a surface for the hydrogen ions and the hydrogen gas atoms to exchange electrons. The solution must contain a solution of hydrogen ions at 1 mole per decimeter cubed, and finally it must be under standard conditions of temperature and pressure, so 1 atmosphere pressure and 298 Kelvin. In order to measure the standard electrode potential of other half cells, they are connected to the standard hydrogen electrode. The measured voltage, called the electromotive force, EMF, is a standard electrode potential of the half cell. The slide shows the standard hydrogen electrode connected to a zinc 2 plus zinc half cell. A wire connects the 2 electrodes, allowing electrons to be transferred between the 2 cells. A high-resistant voltmeter is used to measure the potential difference between the 2 half cells. The whole setup is known as an electrochemical cell. A salt bridge connects the 2 solutions, allowing ions to be transferred between the half cells. A simple salt bridge can be made out of a strip of filter paper soaked in a solution of an ionic compound that will not react with either of the half cells, such as KNO3, potassium nitrate. The zinc has a greater tendency to lose electrons compared to hydrogen. The surface of the zinc electrode becomes more negative than the hydrogen electrode because there will be a greater buildup of electrons as zinc atoms turn into ions. The voltmeter measures the difference in charge between these 2 electrodes. The measured standard electrode potential of the zinc 2 plus zinc half cell is minus 0.76 volts. This is known as the electromotive force of the zinc 2 plus zinc half cell, the voltage produced when compared to the standard hydrogen half cell. This next slide gives you further details about this cell. A negative standard electrode potential shows that the electrons flow from this half cell to the hydrogen half cell. In this case, they flow from the zinc electrode, where the oxidation reaction occurs, with zinc atoms turning into zinc ions and losing electrons, to the hydrogen electrode, where hydrogen ions gain electrons and form hydrogen gas, according to the equations shown on the slide. The overall cell reaction can be shown by combining the two half equations. You need to be able to recall the definition of the standard electrode potential. This is one definition. The standard electrode potential of a half cell is the electromotive force of a half cell compared with the standard hydrogen half cell measured at 298 Kelvin with solution concentrations of 1 mole per decimetre cubed and a gas pressure of 100 kilopascals or 1 atmosphere pressure. Any other half cell can be set up in a similar way and compared to the standard hydrogen cell. The reading on the voltmeter will give the standard electrode potential for that cell. If you have a solution of two ions of the same element in different oxidation states, such as Fe3+ and Fe2+, you can measure the standard electrode potential of the equilibrium set up between these two oxidation states by using an inert electrode such as platinum, which provides a surface for the electron exchange to occur. Again, it needs to be standard conditions, and the solution needs to initially have a 1 mole per decimetre cubed solution of both ions. In order to understand standard electrode potentials, you need to realise that if the standard electrode potential of a half cell is negative, then that half cell will give up its electrons, act as the reducing agent, and oxidation will take place at that electrode. If the standard electrode potential of a half cell is positive, then that half cell will accept electrons, act as the oxidizing agent, and the reduction will take place at that electrode. The table on this slide gives some standard electrode potentials for different metal half cells. The half cell reactions are always written as reduction processes. There is a gain of electrons. Metals at the top of this series, those with large negative electrode potentials, readily give up their electrons and are powerful reducing agents. Lithium solid, LiS, is the most powerful reducing agent shown in this list. Towards the bottom, the species are less likely to give up their electrons and become stronger oxidizing agents, more likely to accept electrons. Au3+, aqueous, is the most powerful oxidizing agent shown here. It can be quite difficult to take all of this in and work it out in an exam situation. It's quite easy to get confused. It may be helpful to remember some key trends. Negative electrode potentials, more likely to lose electrons, better reducing agents. Positive electrode potentials, more likely to gain electrons, better oxidizing agents. Here's an example. Arrange the following in increasing order of oxidizing strength under standard conditions. Potassium manganate 7 in acidic conditions, iodine, iron 3, oxygen in acidic conditions. The standard electrode potentials are given. You do not need to learn any, but always remember they are given as reductions. Pause the video and have a think. The next slide will give you the answer and an explanation. So oxidizing agents gain electrons. The more positive the electrode potential, the greater the oxidizing power of the substance on the left-hand side. Therefore, in increasing oxidizing power, iodine, iron 3, oxygen and potassium manganate 7. We'll leave this here for now. Next lesson we'll move on to predicting cell reactions and voltages using standard electrode potentials. There has been a lot to take in and understand this lesson, so it may be worth watching the video again and ensuring you understand what is going on. We'll review this in class time and answer questions. See you then.